So hello everybody, and welcome to another tutorial. Today we will talk about how you can derive partial charges using quantum mechanics and the program that I've written, which is called multicube. So what is this all about? This program was basically written in order to show new ways how to derive these partial charges without telling you what they're about right now, so you will see this later on. Of course, if you use the methods that I show in here, if you use the multicube program, please cite this article. It will be in the comment section beneath the video. It's also a nice read, probably. Have a look at it, and well, let's see what partial charges are all about, so that you better understand why we have written this article at the time. So partial charges basically are atomistic, or allow you to create an atomistic representation of molecules, at least from an electrostatic point of view. And they describe, well, it's a model, a simplistic model to describe electrostatic properties. It's at a molecular level or at special molecular sites, let's say it like this. And they are, of course, used in molecular dynamics force fields, because molecular dynamics force fields, in most of the cases, they don't use quantum mechanics in order to model electrons, or in order to model the correct, let's say it, electrostatic configuration, but they're an approximation of it. And so you have a charge for each atom normally in force fields, and somehow you have to derive these charges. And this is basically what we will do today. And so what does it really look like? So this big story is basically that in reality, well, you have an electrostatic potential. So all this here, you can derive it from the first Maxwell equation. So basically the divergence of E basically is a source, and you can see that a potential. So if you take this, here the nabla operator on this psi, you get to E. It basically can be described as this here. So you have this electrostatic potential now that you want to have. And basically, normally, well, you have a molecule which kind of looks like this. You have, let's say, an electron cloud, or you have a charge distribution somewhere in space. And of course, you have also here positively charged nuclei from the atoms. But basically, to have the real electrostatic field, or the real electric field, you would have to calculate it like this. And as in the previous tutorial that I've shown you how to render such molecules, well, you know that you can derive this this electron cloud using the Schrödinger equation. No? Yeah. And so what we will do today is, well, you have this and you want to approximate it by this. So basically what you have here is you have atoms, or in force field sometimes these are unified atoms, or some bigger object it's even than atoms, but these atoms or unified atoms or whatever these are, they have charges. Yeah? And so these are spheres in space, let's say it like this, with charges, yeah, or atoms in space with charges. And the question is, well, how can we derive these charges, and how can we make it so that this representation here creates the same electrostatic field as this representation? So what can we do that phi is equal to V? Yeah, that's the big story here. Yeah, so here, of course, as these are point charges in space, you can replace this by this simple sum here, this integral, and sum each point with each charge, and you get to the potential. Yeah, and so the question is, how can I build, using these point charges, a very good approximation of what I get from this? Yeah, and the big idea behind this is that you sample the potential, so that you sample basically phi around here, and you vary these charges as long so that you get here the same V as the phi is over there. Yeah, that's the big story about this. Yeah, so that's what we do, and how we will go for it. So we will model a molecule. So also this was already done in a previous course, so we can do this very fast. And then we derived electrostatic potential caused by this molecule using a quantum molecular representation. So we use ab-initio quantum calculations in order to derive the electrostatic potential of this molecule. Yeah, and then in the end we use our multicube program, so the program that I've written, in order to derive these charges so that they fit to the electrostatic potential that we have derived basically from this. Yeah? That's what it's all about. So how do you do this? So you can use bubble again in order to get a 3D structure first. If you don't have a 3D structure of your molecule, we will do it in the same way as we did last time. So we do it with this, if you remember the 3D visualization, quantum visualization molecular tutorial. So we use Barber in order to, with a smiles code, in order to generate the 3D structure. Yeah? So Barber can do this. It's very approximative, but this is enough in order. Then we can optimize it using our quantum calculations, and this is correct enough for what we want to do. So you need the smiles code. So the smiles code is just as a little rehearsal, is a single line code which describes you the structure of your molecule. So this is more or less a formula in one line which describes you that this looks like this. Yeah, it's a bit complicated to see, but you have here this Wikipedia entry which describes this very well, how this works. Yeah, so here I have the smiles code for caffeine. And with the smiles code, we can generate the coffee molecule. So this here is caffeine. So this is what makes you awake when you drink coffee. For those who don't know it, it's a rather well-known molecule. Printed on T-shirts, and you can find it wherever, everywhere, basically. Yeah. So we already did this, but I will do it quickly again. So we have the smiles code, we generate the smiles file with a SMI suffix, and we use OBabel in order to generate this structure. Yeah, and we get this caffeine XYZ file with the coordinates of our structure. So just to remind you how you do this, so you take your editor, and we call this the coffee. I call this the coffee. It's caffeine, but the coffee molecule, so coffee SMI. Yeah, just like this, a little bit smaller than see me too, and I can write here, and yeah, so this here is the coffee SMI molecule, and I copy paste. Well, I looked it up on the internet. You just type smiles for caffeine and you will find it in 3 seconds. It's not very difficult if you type this into Google. And so here I have my smiles code. I save this. This is saved as my coffee SMI. And I use OpenBabel with this formula in order to generate this tree structure. Yeah, so OpenBabel. So Gen 3D makes a 3D structure, gives me X, Y, Z coordinates minus H. Very important for all what we're doing here is means we add hydrogen atoms to our structure. And for this you need OpenBabel. So if you're on an Ubuntu machine or something, or a Debian machine, you can just type apt-get install OpenBabel in order to get this. Yeah, it's not very difficult. You find all this, you type this in here. I just copy paste this over here. Yeah, because it's caffeine smiles, and I called it coffee.smi. So up, and we have one molecule converted, as you can see, and we have here on our 3D coordinates of caffeine. No? So these are the 3D coordinates that we have derived from this structure. Okay, so right now we have our structure. We could open this in VMD. This is a remote machine, so I would have to copy it over here. I don't do this. We do this later on anyway. We will look at the molecule so that we can identify where each atom, where each of these atoms are. So here we have a carbon atom. This is the XYZ location. This is a standard XYZ file, no? And well, we have to get over to quantum chemistry. So we already talked about this also in this last tutorial. So in order to do this, you need to use this NVChem, no? And we solve the, let's say, an approximation of the Schrödinger equation, of the static Schrödinger equation, where you have basically here kinetic plus potential energy is energy, and this is an eigenvalue problem, and we will find that these are discrete energy levels for this Hamiltonian operator, that is, this is called. Yeah? Not very difficult. We already discussed this in this previous tutorial where we rendered these molecules on a quantum mechanical level. Yeah? So as I said, this is an eigenvalue problem. You have here, instead of eigenfunctions, instead of eigenvectors, but basically that's why you use this bracket notation. And we see here, yeah, this gives you a probability density in space where to find these electrons, and using this we basically can derive this cloud here, no? That's what we want, because we need this cloud in order to calculate the electrostatic potential. So we need to know what is the probability to find an electron in this region of space, because the nuclei, we know where they are here, positioned at these positions. They will be optimized, so of course we can, using this whole stuff, we can vary the positions a little bit in order to get out a better structure, a more energetically minimized structure, let's say it like this. Yeah. Okay, so we got this structure, we got this, and we do our quantum calculation. And our quantum calculation, we do it at the level of theory. So this is the density functional theory. So this is an approximative solution of the Schrödinger equation of what I've shown you before. And we don't go into all the details, just as I told you the last time. If you want to know how you get to this theory, to this B3-lib theory from here, just read my thesis. There's a whole chapter about quantum molecular dynamics in there. And here we just use this B3-lib, so this density functional theory, in order to solve this equation, and in order to generate this electron cloud, from which afterwards we can of course calculate the electrostatic potential. So we integrate all this and we get the electrostatic potential out of it, no? And that's what we want. And so how do we do this? So we use this NVChem, and we have to create an NVChem input file, no? So let's do this together. So the input file looks like this. So we need this start here. So this is just here. This is basically the header. We use 100 iterations. That's pretty fine for what we're doing for these little molecules. This is how much memory we give to this job. 12 gigabytes is fine. We have here a pretty big machine. Type 3 here. So here we have 64 gigabytes of memory in this machine. That's pretty fine. That's why we use this remote machine. And well, let's build this input file. No? So let's do it the coffee input.nvchem file. No? So that's basically it. So you have here my little Emacs, my little editor on this remote machine, and I just copy paste this over here, and let's call this the coffee job. No? Coffee job. No, that's just the name. We can put here anything that we like, and then we need the structure. So the structure is again from this XYZ file. So we just copy this over, and we have to tell them, when if you use this open bubble, this gives you angstrom units. So we just put here geometry units, angstrom, and this XYZ stuff, and we can. Here in Emacs I can open with Ctrl X2. If you want to know it, you can open a second file in here, and I can open the XYZ file. I don't know how we named it, the coffee XYZ file, where we just generated the structure, and we just copy over the coordinates from here to here, and then we write and we have our structure. We have basically our structural part of this NVChem file. No, I will just kill this here and then make this Control X1, and I'm back to my file all alone. So I have here the geometry. Don't forget to write and here at the end of the geometry so that you don't mess up your stuff. And then we have here this job properties definition. So we have to tell, of course, NVChem what to do with our structure. So we tell him, okay, well, you use these basis functions, so this is part of the theory. The basis function is basically in this basis, like a Fourier basis, in which it develops the solutions. Yeah, so this means around each atom it builds these Gaussian basis functions, the 6 Gaussian with this stuff here. Yeah, and then we used, as I said, density functional theory with this Becker's 3-parameter Lie-Yang-Bar set, which is very well known, which is very frequently used. If you want to know more about it, well, read my thesis. Up there are all the descriptions where this comes from, and basically the citations where this piece really comes from, if you're interested in that. Yeah, it's not that important here, it's just here it's used in order to derive this electron cloud and in order to get the electrostatic potential, and for small molecules it will be fine if you do it that way, probably. Yeah? And so we have this, so then we tell basically the story that, okay, you use this basis function, you use this level of theory, and then we tell it, well, optimize this stuff here, no? Optimize the molecule, so this makes basically a geometry optimization, so that our molecule is more correct than this approximate open bubble representation that we have derived with very primitive force fields that are used in open bubble. Here it's a quantum calculation, and we minimize the energy of this molecule in order to better place the atoms in space and in order to evolve these coordinates that are in here, no? Okay, and once we got this, well, we have this property here, and this property means electrostatic potential, so ESP, electrostatic potential. And we generate, just like the last time, a cube file. Here it's not -1. This is a different notation in NVChem. Don't ask me why they use different notations for different types of cube files. But if you calculate the electrostatic potential, well, you have to do it like this. So you basically say, okay, you calculate the electrostatic potential. You want it on a grid. And you want it from -10 to 10 angstroms around this molecule here, around the origin, and we want to have 80 grid points. Yeah, that's pretty fine. Yeah, so if you do 250, it already takes long enough with 80 grid points, 80 in all directions. You can also use here asymmetric cubes if you think that's a good idea. Here I do it symmetric. The more points you have, maybe it fits better. 80 is more than enough for what we're doing here. Now, okay, takes already long enough. So I prepared most of the stuff because it takes hours in order to calculate all this. So then we get the coffee cube. So this is the output file that we get, and then we get the cube file, as I told you last time. So where we store, what we do here is we get this molecule here, and we build a cube around it, which is 10 by 10 by 10 angstroms long, and in each, so we get 80 points in each direction here, so 80 by 80 by 80, and in each point we store, in, let's say in each voxel, we store so this psi in this cube, yeah, and that's basically what we can do. Then we can use this here in order to recreate such a cube and to calculate the difference between these two cubes, and then fit these differences, so minimize this difference in order to get this V out, and that's how it works. Yeah? So let's go back to down there. Let's go back down there. So we're down here, and we do this, and then we run this job here. So I copy this over here, so I already prepared this here. So I have here a footer file. You just you can't copy and paste from the video. Maybe I'll put it beneath the video. If not, you just look at the screen, or you just put it standby, and I open here. I have here a footer. No, footer. So I call it footer here, and this here is basically the. So what I need here is this basis part and this here, no? So yeah, that's what we need. So okay, and right now we got everything. So we got our input file. That's all that you have to do. So that's all that you have to do in order to create with any Smiles code an electrostatic potential grid for your system. No? So we got this, and right now you can run this. I already did this, so just to show you how you run this. So you type nvm and you type coffee input, and it begins to run. Yeah, and I will stop this because I already did this, of course. Yeah, because this here right now runs for 1 hour, and then you get your coffee ESP cube out, and that's all we need. Yeah. So this runs for 1 hour, and you imagine that right now, as we did this, that in this file here you have your you obtain the coffee ESP cube. Yeah. So I already ran this because it runs, well, maybe not for an hour, but I guess for at least for 15 minutes, if not longer. So that's not very interesting, and I have here a tutorial folder where I did all this, and we have the coffee ESP cube here, no? So that's the file that we want, and as this is a remote machine, I will copy it over, so that I already did this already, so I already copied this over to my machine, and you can do this using SCP, no? But if you do this on remote machines, and we have here the how do we call it? The coffee cube, no? So if I do here vmd coffee cube, ESP cube, I got my little molecule here, and we have in here basically our electrostatic potential around it with all these little values. Yeah, we won't visualize it here, we just have it here. So you just imagine there's a cube around it, and you can visualize this here, as I showed you last time with the electrostatic potential. Maybe we do this very quickly. So if I go here, draw style, drawing method, no, it doesn't. Let's leave it here. Yeah. So we have here this molecule, and basically, if you go there where I've been before, you can visualize this electrostatic potential around it. It's not that important. We already need the cube, and from this cube we can basically derive this stuff. What we need VMT more for is that we can use here O, and that we can select. So if I take my terminal that I've opened VMT in, and that we can select each atom so that we know where each atom is. Yeah? That's very important, because I need this in order to build my input files for the multicube tool then afterwards. Yeah? Okay, why do I need this? Well, let's go forward to multicube. Yeah? So, multicube. Multicube is right now our partial charges derival tool. Yeah? So multicube, you get it here on GitHub. So you head over to this website, and if I click here, I hope my browser opens, or it doesn't. Why is it? Oh yeah, it opens. It opens 3 times. That's nice. And we have here this multicube program. So how can you get it? You just go here, and you can obtain this here using Git, of course. So you just do git clone as in the previous times. So I do it here in the tutorial folder for you. I already compiled it here, so I have here my multicube stuff to show you this. Yeah, as I told you, because all this takes a lot of time, and we want to make some shortcuts here. So let's go into this tutorial folder and let's compile this for you. So what you need to do is you need to git clone, and you have to have this multicube here, and you have it, and you go into the multicube folder wherever you cloned it into, and here you have your file, and you have to compile this multicube C file. Yeah, so in order to compile this, of course, you need several tools, and one of the tools that you need here is you need OpenCL. Yeah? So this stuff is written in order to take graphics cards into account, so it basically does all the calculations on the graphics cards. Because it's rather sophisticated, and it takes a lot of time to derive these partial charges in the way we do it, and therefore, you better have a machine which has a graphics card. I mean, it doesn't work. It does, of course, also work using CPUs. You can read it in the manual. You have to change some little things in this file here in order to get it to run with CPUs and with an OpenCL implementation. So you install OpenCL on your machine. If you're on macOS, you already have OpenCL, so it should basically just compile. You read the instructions; they're a bit different. You have your README file; they're a bit different than the normal compilation. If you don't have OpenCL, you can either install the Intel Compute Runtime. You look this up on the internet and you look it up how you install this for your machine, or you install the NVIDIA CUDA toolkit if you have an NVIDIA card. So if you have a newer Intel processor, you can do it like that. You can install the NVIDIA CUDA toolkit. There is probably also an AMD solution with AMD drivers in order to get OpenCL running on your system. Even if you have OpenCL 1.2 or something like this, or old versions of OpenCL, it should work because the program is pretty old, to be honest. So this all should work. You need to install a C compiler. A C compiler, it's apt-get install build essential, something like this. Something like this. You will find it for if you're on Ubuntu Debian, something like this. In order to install the NVIDIA CUDA toolkit, you type on the internet Ubuntu or whatever you're running on it, NVIDIA CUDA toolkit, and you will find the instructions in order to install this. So you need those two things. And once you have those two things, well, you can run multicube on your machine. Okay, so let's have fun with multicube. So what is this multicube all about? So it fits charges using a gradient descent, so that, of course, that this phi becomes this psi. So as I told you, we have here around in space this electrostatic potential, and we basically vary this q's here using a gradient descent, in order to obtain the same stuff as here. And the stuff that is so interesting with multicube is that you can use basically any type of loss function. So the question is how you calculate the difference between this cube and this cube here. And we have shown in our little article that we have written here above here that if you use the L1 norm, that this works way better than if you use the L2 norm in order to derive these partial charges. So that's the whole magic behind it. So this is what I tell here. So we have this L1 beats L2, and so using this multicube program, you can use the L1 norm or anything else. You can build your own norms with maybe let's say a lasso or ridge regression type norm in there in order to do this. So how do you do this? There are built-in 4 norms. Just if you don't know what to do, you just use the first. It's the L1 norm, and you're well to go. So all the other programs basically that do stuff like this, they use the L2 norm because you can directly calculate it, and it's very quick. But we implemented this on the GPU, and that way you can use other norms, and it's very quick too. So, and the second thing that you can do basically is you could use more than one conformation. So here I've shown you. We used OpenBabel in order to generate one molecule, and so we have one cube with one electrostatic potential, but in practice you might have molecules that have different conformations, and you want to have these partial charges, for example for a force field that you want to use in a molecular dynamic simulation, that works with all types of conformations that this molecule can get to. So you generate multiple cubes with different XYZ files, as I've just shown here, with n by m, and you can then use basically these multiple cubes on one, or if you have a machine with multiple GPUs, in order to get one charges set which fits them all. So you have then one charges set which is basically a trade-off between all these different conformations of your molecule. Something else that you can do is you can do different rotations and stuff like this. It's not that that doesn't really help, but what is really interesting is if you use different conformations of the same molecule in order to derive your partial charges, for instance, for molecular force fields. So that's what you can do. Okay, so let's get practical. How do you run your program? So first of all, you have to compile it. So if you have your C code here, you can use GCC, and you have here a special command which is written here in the README file. So you can open here, of course, the README file in the folder here, or we do it in GitHub here where it's already written down here. And when you write this, don't forget this D double, because otherwise you get the single precision version, which does not work very well. So the single precision version works for very small molecules, like if you want to get partial charges for a water molecule with 3 atoms or something like this, then it probably works. We implemented this to test this, because at the time when I've written this code, most of the GPUs were single precision, and of course then you went to the high-end compute clusters which had these double precision GPUs, and this was the cool stuff at the time. But if you wanted to test this at home at your graphics card, you had to write this in single precision first before you can go to the big cluster where you had some compute time in order to run this. So use this D double switch. Don't forget this in order to get the double precision version. You just forget the single precision version. It's more or less for the developers. So this is your code. So this is basically links to the OpenCL library. It depends probably on your distribution, but in most distributions this will work. If you do this on a Mac, you have this OpenCL framework. So you write framework OpenCL. This should probably work. And you compile it like this, and you get GCC from the Xcode, whatever developer tool, something like that, or you use Clang here, instead of GCC in modern versions, Okay, so we copy this and we paste this here, and we get our multicube program, And forget these warnings. These are unreturned values from some function. That's not very important. You have here your multicube program. We compiled it with the double precision stuff. That's important that you use this D double. If you write it wrong, you get the single precision version. So just write it correctly down here. Okay. We have the double precision version, and right now you have basically already an example here. So you have this HCN example with a cube with van der Waals values and charge values, but I will walk you a bit through how you can do this for your let's say for your coffee molecule. So what you need is a charges file, which is just an input file where you describe all your, so this is basically the starting point for your optimization. So you vary these charges as long until the field generated by these atoms is the same field as the one generated by the quantum representation where you have an electron cloud. So you need a starting point, which are the values for each atom. If you don't know it, just put 0 everywhere. If you're a neutral molecule, because the initial charge, the total charge is basically kept constant. So if you want to have a molecule which has charge 2, something like this, which is a charged molecule, well then you put a total charge in which corresponds to the total charge that this molecule has. Otherwise, just put 0, and if it's 2, well, you just put one atom or the value, and it's fine, probably. But if you already have a bit of an idea where the charges could be, well, then it saves you a bit of time. That's the story. Okay, and it might converge faster if you have a nicer starting point. But 0 is a nice starting point for a neutral molecule, let's say it like this. Okay, so what does this look like? So we have our, as you said, we have in VMD our molecule that we have opened here. And as I said, if you type 0 in VMD, this cursor changes to this, the way it looks like here right now, And then with the terminal we have opened VMD, you can identify your atoms and you know where they are. So basically they have this index here, no? So if I go here, for example, at this N, it says index 1, and if I go to this carbon, it has index 2, and this one here is index 0, And so you know, okay, with these indexes, you know where they are in your file, which is important because we have to put them in the same order as they're in here. And so what you do is we open this cube file, or we have this cube file already here. I have it here on my disk, or here in this tutorial folder. We have it here, the coffee cube that we obtained using our NVChem file, which is this coffee ESP cube here. No, that's basically what we have obtained from our calculation that we interrupted because it would have taken an hour. So if I type here N, let's say 30, something like this, coffee cube, of course, then we get something like this, no? Well, let's do 35 so that we can display it all. Yeah, okay, so here these are the values of this electrostatic potential down there, and this is the cube file, and this is this cube file atom position. So here we have the positions. That's not that important, but what's important is that we have here basically a carbon, nitrogen, carbon, nitrogen, carbon, carbon, oxygen, nitrogen, carbon, oxygen, nitrogen, and we have this basically in that order, and this should be the same order as we have put it in the input file. So when we go back to our NVChem input, so we have it here. So you see here carbon, nitrogen, carbon, carbon, oxygen, nitrogen, carbon. Should be the same here. Carbon. Exactly. No, nitrogen, carbon, nitrogen. Interesting. Nitrogen, carbon. He probably reorders this in order to get it better for his stuff, or this was ordered differently here, but that's basically this cube here, And so, as you see, you have to be careful, that you get this and it's in the order as it's in the cube then, That's the very important thing, So what you need to do is basically you copy paste this. This is the easiest way to do it, And you create a new file with this, So I will do it here locally because I already generated this file, but over there, of course, just to show you how you can do this. So let's open Emacs and open a new file and call this the coffee charges. So we need this charges file. So this is the first file that we need, and I copy what's going on here, and I copy over this stuff here. Okay, 6, 1, that's fine. We start with 6, we end with 1. I hope we got everything. Should be fine. So what I will do first of all is I delete all this here. So using Ctrl X and space, I can do this rectangle select mode here in Emacs, and I can just then with Ctrl V remove this. You can do this probably with your editor in the same way. I will do this here 2 times, and do this that way. And what I then do is basically that I order this in with numbers, yeah, so that I know which atom is where. Yeah, so 6 we know it's a carbon, so this is carbon 1. Yeah, carbon 0, let's say like this. Yeah, this here is N1, this here is carbon 2, this here is N2, N3. Yeah, so use the numbers just from 1 to over there. Yeah, carbon 4, carbon 5, carbon 6. Yeah, oxygen 7. Yeah, nitrogen 8. Yeah, carbon 9. Yeah. Oxygen 10. Yeah, do I have it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Perfect. Yeah, nitrogen 11. This is a carbon 12, carbon 13. And then I'm with my hydrogens here. Yeah, so hydrogen 14, 15. Sorry for that. 16. This will be pretty fast. Let's do it like that. And we have basically our basic input structure of this file. Yeah. The stuff with this here is that the way you can name this any way you want. Yeah. So you can name these atoms. So these are just the atom names. Yeah. And behind them you write some input charge. Yeah. What the charge on this atom in this cube file should be. The big deal here is that we probably want to have atoms to have the same charge. Yeah, and if you name them the same in here, and then use them in this van der Waals file that we will talk about afterwards, you get you can do basically these fields that where you have basically for several things the same charge. So let's say it like this. Yeah, we want to have these methyl groups here. Yeah, so these carbons here with these 3 hydrogens. Yeah, so here, and yeah, so that they have the same charges. So we want the carbon to have the same charges, and we want to have the 3 hydrogens to have the same charges. Yeah. And that's here why I numbered it this way, because if I do this that way, you have of course to look in your cube file that you have generated with NVChem, that you have this output here, yeah. You can then select them here in VMD. If I find my VMD terminal, I'm sorry for that, so my VMD terminal is here. And right now I don't find my other terminal, but that's the way it is. No, that's the way it is. So that's here my terminal. That's this terminal with the cube file. Where's my Emacs? Where's my Emacs? So there's like coffee charges. That's it here, yeah. So if I numbered it like that, I can click here. Yeah, it's all messed up here, but that's the way it is. So and if I type 0, then of course the cursor changes to that. And if I click here, for example, so I know that this is carbon index 0. So this is the first one here, yeah? If I click here, I know this is 12, so this is the C12 here, yeah? And if I click here, this is C13, so this is the C13 here. And if I click at this hydrogen here, I see this is H19, so this is the 19th hydrogen here. And that way I can find my way using VMD around writing this charges file. And so what I want to do here is, for example, I want to have the C0, yeah? C13 and C12 have the same charge. Yeah? So let's do this. So what I want to do here is I call them CM, yeah, for carbon metal, whatever you want to call this, yeah. CM. So this is CM. So we said then C13. C13 is a CM2. Yeah, okay. And as they have the same name, they will have the same charges afterwards. Yeah. And this here is C12. So C12 is a CM2. Okay, what else do I want to have the same charge? So I want to have, let's say, Yeah, the two oxygens, do they want to have the same charge? Yeah, let's have the two oxygens. Probably not in reality, yeah, but I guess that's the way I calculated it last time. So let's say we want to have these two oxygens the same, so this is oxygen 7 and this is oxygen 10, so we already know where this is, so we can just call them O, let's say it like this, yeah. And then we want to have these hydrogens here around the carbon files the same charge. So this here is hydrogen 14. Yeah? So hydrogen 14, I call this HCM. Yeah? So because this is the hydrogen which a link to this with those here. Yeah. So that's 15 and that's 16. So 15 and 16. Yeah. And then I'm going down here and I see this is 20, 19, 18. So it's not 17, but this is 18, no, yeah, 18, HCM, and 20, no? And that's the way it works, yeah? And then I click over here, and here I see this is 21, 22, and what is this one here? 23, yeah? So HCM, and now you see how you can use this in order to derive charges for force fields, because the story that what the program then will do is basically that CM and CM will have the same charge. Yeah, it parameterizes it that way. Yeah, and also everything which is different, which is named different here, will have a different charge. That's the way it works. Yeah, that's as easy as it gets. Yeah, and then you basically, as this is the charges file, you have to put the charge here, and we said, yes, 0 is fine, so write 0.0 so that you don't get into integer problems. I don't know, probably we won't get there, but I don't actually remember how I parse this file, but that's what you can do here. You can just do 0.0, and I use this Control X trick here that I have here in Emacs, and I get to this 0, 0 everywhere. And it works because, yeah, I just switched over to the other one. Doesn't matter, but that's basically my file. Yeah, here I named this OC and not OO. Yeah, that's the way I did it. Yeah, so these are basically these ESP charges. Yeah, okay. So once I have these ESP charges, yeah, so you have to write this file. What you have to be careful here is that you don't end here with a return. So if you put the return, just efface it so that this here is really the last character here. Yeah, so that this doesn't end on a new line, because otherwise, the way this was written, this doesn't work. So with this file specification is that the file ends here after the last thing. Yeah, you have to use this tool that way. Otherwise, it won't work. Okay. So here you have your charges file. That's the first thing that you have to prepare. The second thing that you have to prepare is the van der Waals file. So the van der Waals file is the same, it's a bit like this, but you only put for each stuff that appears, you put it once. Yeah. So let's do the van der Waals file. Yeah. I probably already have one, but okay, I show you what it looks like, yeah, to make it a bit shorter. So van der Waals file. So that's the van der Waals file. That's the second file that you have to create, yeah. And so for each atom type that you find in the first stuff, so you begin with CM, and if you know it's a second time, then you just forget it, yeah. For E, but you have to put down each atom type at least once, yeah. And in the right order. But you have seen it over there. So if you have this, you start with CM, N1, N3, and so all these you take them, NOC once, yeah, N8, then you have another OC, you just leave it out, yeah, then you have another CM, you just leave it out, and then you have just one HCM and H17, yeah, and that's exactly as it's done here, okay. Very easy to do. You write this by your hand, yeah. You find these van der Waals values if you don't know them. They're easy to find. They're even on Wikipedia. So Wikipedia van der Waals radius. So why do you need these van der Waals radiuses? Yeah? very easy to tell these van der Waals. So here you have these van der Waals radios. I just picked them from here. What they do is they just screen out all these voxels which are in close proximity to the nuclei, yeah? So that you don't get very crazy high charges. They are high potential terms basically that you fit to. This screens this out here, yeah. So you screen out around each atom these points, yeah. So like here, yeah, and here basically you don't take these points into account, yeah. That's the whole story behind this, yeah. So to get a bit out of the electron cloud, and to get a very nice potential here to fit, yeah. That's why you use this van der Waals story here. You can make them a bit bigger if you want to. It doesn't matter, yeah. You just use the values that are down here as I did, and that's fine, yeah. Okay. If you have different atoms, well, you have to find them. They're published. You will find them. You just look it up on the internet, van der Waals radius of your atom type that you want to have, or in your force field parameters that you want to describe if you have this. And that's the way it is. So then we have this van der Waals file, and we have our charges file, no? And right now we can run multicube. So running multicube, if I can back to my terminal, my terminal is this one here. I probably have closed it. No, it's still here. So here's my terminal. And right now we can go into multicube. So I did this here. And you can run multicube. So how do you run this? We have here a lot of stuff. So it's described very well here in the browser. I just wanted to search it here. Let's do it like that. That's the easiest way. Yeah, so that's how you run it, yeah? So you run multicube, okay? And then we look it up in the browser at the same time, so that I remember how this was all run. Then you use your charges file, the charges file that I told you. Then you use this van der Waals file that we prepared, yeah? Remember, in the van der Waals file, there are only for each atom type one van der Waals radius. It uses this also to count how many atom types you have, yeah? So it's very important to get this right, to get this the way we did it here, yeah? And then you have your charges output file, so where you write your charges down. This is the norm that you want to use. So one is L1, then the number of GPUs that you have. What was the third value? I have to look it up. Hang on a second. So multicube. So it's here in my GitHub repository. That's the address. You clone this. That's where you get it from, yeah? And here basically it tells you what is what, and so as I told you, so that's the initial step size, yeah? So the initial step size is the one here, 1 point. This is a floating point value, that's why we put a point here, and then these are basically the deltas in the derivatives, yeah? So you could calculate them with machine epsilons, whatever. These are fine, yeah? So how does this look like? Yeah, so one is used in the gradient, and the other one is this. So the second one is this convergence criterion. Yeah, so you have used these two values. If you use these two values for typical molecules, you will get a very nice stuff. You could use for the convergence criterion. You can use higher values even if you think it takes too long. Because if I run this that way, it takes at least an hour for a coffee molecule. And I'm fine with that, but maybe you're interested in less accurate charges, it doesn't matter. So this is how many steps you want to use. So here I aimed for 100,000 steps. I could use, we can use more or less if you see, okay, this didn't converge, but this just counted all the steps down here. And then you have the coffee, then you put your cube file here. Or you can, of course, use, as I just told you before, you can use multiple cubes in multiple conformations. So you just put as many cubes as you have down here. Yeah. Of course, if you have one cube, you can only use, I guess, one GPU, because the way it works is it distributes these cubes around the GPUs. If you have more cubes and more GPUs, you can use more GPUs here, and it might work. Yeah. With one GPU it works, it's tested. With multiple GPUs it was programmed so that it worked on the clusters that I've used this. I don't guarantee it works with multiple GPUs. If you're not sure, just put one here, it will be fine. So this is a pretty fast GPU in here, and just to tell you, for the coffee molecule it took about 1 hour, 1.5 hours in order to derive these partial charges. I guess even more, maybe 2 hours, don't remember actually, but it took pretty much a while. So if I run this here, I will just copy the charges out file so that I can show it to you without running this, because I already run this. Let's call it save. Yeah, so this is just the charges out file that I've obtained in running this just before. So just to show you, this machine here has an NVIDIA GeForce whatever machine here. It doesn't tell what type of GPU it is. It's the GeForce ... but it's a pretty fast one. Let's make this a bit bigger. Maybe it tells us then. No, it's the ... GPU. Doesn't matter. I don't remember. 1000 whatever. It's pretty fast stuff. Yeah, it has 12 gigabytes of memory. As you can see, it consumes 170 watts, so it heats my little workplace. But if I run this here, as we just had it, now I put NVIDIA SMI so often in here that I don't find it anymore. Let's scroll a little bit back to our stuff. Here's the multicube. That's the command. As I told you, if you don't know the command, here it is. So you just basically, all you need to do is you replace your charges file with the HDN charge, the HDN van der Waals, the charges out file, and here you put your cube. Yeah? And you leave these parameters as they are. It's fine. Yeah? If you don't know what you're doing, that's perfect. Yeah? That's the way it works. Put maybe more iterations if you see you hang on at the iterations here, especially if you have large molecules where this might take a long time. But that's the way it is. Yeah. So that's the other values are basically that I put them in when I developed this. Yeah. So let's get back here. And I wanted to do copy paste. Come on, what are you doing here? So let's do it like that. Yeah. So let's do it like you would do it. I just copied this here. I paste this over here, and I replace this here with the coffee stuff, with the caffeine stuff. So we put our caffeine charges, as I told you. So this is ESP charges. So that's the charges file that we've just edited before. Yeah, so where you have all these values in here, we use this ESP van der Waals file that we also told you about, which basically screens these values in close proximity to the nuclei. We define our charges out file. We can call this charges out. Yeah? And here we put the cube, the coffee cube that we have obtained using our NVChem file, our NVChem drive. And then you start this, and then of course it puts a lot of stuff out here, and it runs maybe for 2 hours like this. And that's the way it works. Yeah. So these are basically the iterations of the gradient descent. And the gradient descent might be a bit slow because it has to do a lot of projections in order to keep the charges correct and all this stuff. But that's the way it works. Yeah. And it does this in the L1 norm. Yeah. So if you want to do this in the L2 norm, you replace this first one here by 2. As I said, L1 norm charges, they take longer to derive, but they are faster. Yeah. And if you kill this program just as I did, so you can also do this if you run this on a cluster. So if you send it the signal that controls C sends, I guess it's sigint, yeah, then it also writes your charges out. So we call this charges out here, and it tells you one got killed, and you can use these charges as input charges in your charges file. in order to continue. Yeah. Cool stuff, no? That's the way it is. But so that's the way you calculate this, and here it runs, and it would run. So I had this running for 2 hours, and then I got my charges out. And what I obtained is this charges file here. So the one that I've shown you before. Save. And these are basically the charges for each atom. Yeah. So if I want to know where they are, if I have forgotten that, so the way it is, as I told you, just open the cube file and you copy paste, or as we built this with this charges file, you can use the paste command. Yeah. So the paste command basically puts columns from files next to each other. So you type your 2 files and you get them next to each other in Unix if you don't know this command. And you have here, we had the coffee. So these were the input charges, yeah, the ESP charges. And then if I go to coffee charges out, so this is basically the file that this program writes when it stopped, when it finished, when it went to this convergence criteria after 2 hours, as I told you about this runs. And here basically see, okay, so CM has this charge, yeah. And as you did this before with VMD, you know where CM is, which are the CM atoms, where is N1, where C2 is, and you know, okay, these things will have those charges. And that's basically it. And that's the way you derive partial charges using quantum mechanics and using my multicube program that I've shown you with this tutorial. And I hope you have fun with it, and have nice holidays, and I wish you a Merry Christmas, as tomorrow it's Christmas. So that's all for it this time.